Okay, so 3, 2, 1, go.
Now, I will tell you this. Most of the time I've seen these, not all the time, sometimes they do give you the pKa. Most of the time they'll give you the Ka. So this first step where I'm taking the pKa and I'm going to Ka, most of the time you don't have to do that. So that's a happy face, right? But if they give it to you, you know what to do. Very common to see this pKa value in a chart with other acids, and they're going to say which one's the strongest one. Or, the stronger the acid, the weaker the conjugate base. They'll ask you, I give you a bunch of pKa values, you got to take that in your mind, flip it around, and then think, okay, stronger acid, weaker base. It's fun. Here we go. Anyway, so, like, there's formula sheet, that's fine, but just talk yourself through it. pKa, I can't do anything. I need the Ka, I need that equilibrium expression, I need that constant so I can set my fraction up with my little brackets and call it a day. So P means negative log. So the negative log of Ka, see how I'm talking myself through it? That's what P stands for, is 9.31. And so again, I got to isolate my variable fully. So I'm going to go ahead and divide both sides by -1. And most books skip this step. This PowerPoint skips this step. If you skip this step, your answer is going to be super wrong. Okay, so anyway. So now I have the log of Ka is equal to negative 9.31. And to make that log go away, I'm going to raise both sides, make them powers of 10. So I have Ka is equal to 10 to the negative 9.31. And I'm going to put this in my calculator, and then I'm going to write the exponents down too this time. Okay. Y'all catch me, I'm definitely prone to mess up. Alright, so I got basically 4.90. So my Ka is 4.90 times 10 to the something, and I walked away and forgot. Negative 10, okay, cool. So, this is when I take my products in brackets and put them over my reactants in brackets, this is what that fraction has to equal. Okay, so we got to keep in mind where we're going with this. So, okay, cool. Most of the time, you're going to start here. So that's half the times. Alright, so let me move on, and I'll show you their pretty work. Much simpler. That's fine, but like May 2nd, are you just going to remember, oh, I'm just going to pop that up on a 10? No, probably not. So I like to show you the steps. That's what they got. So I am going to go ahead and work on an ice table. And so, you know, my Ka expression for this, I always like to have that in the back of my mind. Let's see, where do I have room to put it? Ka is equal to, so my two products, so I have, and I'm just going to put hydrogen because I don't have a lot of room. And then Cn, right? I still ran into that really badly. And then HCN. So there's my products, there's my reaction. So that looks really bad. I'm so sorry. Do you know how to do that part? Okay, sorry. I'm looking at this, my molarity or my concentration in the brackets for HCN this time is 1.5. Yeah, that's easy. And then always these are going to start at 0. That's not true. They don't always start at 0. That's another day next week. So minus x, because my coefficient is 1, plus x, plus x. And so you kind of start to see this pattern where you can always ignore this x, and this ends up being x, and this ends up being x. Yes, it is always going to be like x squared over the concentration of the weak acid. I don't want to just tell you that. You're going to show you work. You can't just pop that out of nowhere. You're going to show our table. So if you get something different than that, though, then you can kind of check yourself. Anyway, so there's my little ice table. And so my equilibrium expression, the 4.70? What? Let's see. That is equal, basically, I got x squared over 1.5. And so that's what I just did. I'm gonna rewrite that probably on the next slide to give myself some room. So there's the numbers in prettier font. You got all that down? And this is just to find the pH of a weak acid base. Don't you wish they were all strong? Wouldn't that be better? Yeah, that'd be super. Okay, so let's go ahead and fill in the whole thing. So to equal x squared. Do you know where I got x squared from? It was x and x, okay. And then the number was it 2? 1.5? 1.5. Okay. Sorry, I've done so many of these problems. So I'm going to solve for x, and the first thing I need to do is isolate my variable. And so I'm going to multiply both sides by 1.5. Whatever I get over here is going to be equal to x squared. So times 1.5. Still in my calculator. So I got 7.35 times 10 to something, 10 to the negative 10. So to solve for x, I'm going to need to take the square root of both sides. And so x is going to be, so 2.71 times 10 to the negative 10. And I'll stop there and kind of make sure that you're all with me. Now that is equal to x. If you ever feel like in chemistry you're done when you get what x equals, you're probably not done. I can't think of an example when like the letter x is the end. Because it's like you might solve for mass and you like m is equal to something. So x was actually equal to my hydrogen or hydronium ion concentration. And so now I'm going to go in here and I'm going to solve for pH. So pH is equal to the negative log of my hydrogen ion concentration, which was this. And so pH is going to be what my friendly calculator tells me. But no, seriously, before you use your calculator, don't use your calculator yet. I wanna make you use your brain. Eyeball that. Just kind of eyeball it. What should the pH kind of be close to? 4, maybe like 5. Okay, and I can see why you'd say 4. Okay, in your mind, you got to think about it like this. You have to be able to do this in your head, okay? As this number gets bigger, 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 up to 10, that's going to turn into a negative 4. So it is between 4 and 5, but it is closer to 5. So it's probably like 4.7. I'm guessing. I have no idea. So what is the answer? 4.56. So 4, okay, fine. So, but do you see, I mean, I'm not magic. That ain't that bad. Like, but you have to be able to do that, and some people just can't do that. I'm not. Just gotta, and I'm going to show you how to do that in your head. Like, you know, sometimes you just, in math, you just take and plug stuff in, and you never have to think. You have a calculator that does it for you, but you don't get that calculator in that first part. And there's nothing you can do on a piece of paper to make this work other than up here. There's nothing you can show for that. There ain't nothing for that. Anyway, so there's that one. Okay. It's really not that bad, right? Okay. I think it's okay. Alright, so let's look at their prettier work. And we can assume it's, yeah, we can always assume. And that's what they got, so I guess we're good. I'll tell you about this percent dissociation. The thing about on the AP exam with percent dissociation, like a strong acid is going to dissociate 100%, and a weaker acid may be much smaller than that, and they'll tell you. But I've never seen or had anybody tell me or seen a practice exam question where they say an acid dissociates 3.7%. I haven't seen that. So guess what I'm not going to do right now? I'm not doing this. They're going to ask you which one has a higher percent dissociation based on the Ka value. Larger the Ka, stronger the acid, higher percent. But doing this I think right now ain't going to help you understand that. So I'm not wasting my time. Like in April, if we decide we want to do this, like let me know. But I've looked at every release exam question, and it says that on your learning objective, it says that you need to be able to differentiate between percent dissociation and acid strength. They don't say you need to calculate it, so not doing it. But you know, it dissociates 0.767%. That's pretty weak. So that's why you can have vinegar on your I don't know, French fries or whatever, salad, whatever. And so x right here minus x, you just use a percentage. See, they multiplied it as a percent. Or, excuse me, as a decimal. You took the decimal to a percent. And then they found x, and then you can take 0.300 minus that. It's not hard. I just ain't doing it. So, anyway, same thing after this part. So this is something different. You do these the same way. When we're calculating the pH of a weak base, we're going to do everything the same way. And look here. See? They give you the, if you don't know AP exam, like, I don't know, I don't remember anything. And so ammonia, the base, or an acid, I know that other one is the different one. You don't know. Well, just fine. They're telling you the answer right here. It's a base. So anyway, you're going to do all this work, and you're going to find everything just the same. But when you go at the end, you're going to use the hydroxide ion concentration. We'll find POH, and 14 minus POH is a pH. So it's real easy. You just got that extra step at the end, and this is where you're going to use your brain. When you get a pH, it'll be the POH, right? You get that POH at the end, it's a base, and you get like 2. Oh, that ain't right. So that's where you have to think about it too. So we're going to do everything the same way, but at the end, we're going to have to subtract the POH from 14. So here we go. Do y'all want to try this first part here with find the KB for me? Go ahead. I need some coffee. This freshman sucked the life out of me and stole my coffee break. I think it stabs. It's good. This card is gone. I'm fake crying, but I'm actually sad. I don't think y'all understand. So I just want everybody to get the KB. You don't have to keep going. You probably could figure out the rest, but you know, this is the last one I'm doing, so just like savor it, savor the moment. All right. So here, check your you got your PKB. All right. So check your work. 1.8 times 10 to the negative fifth. Do you get that? Cool. So that when I set up my phase equilibrium expression, that's going to be what it's equal to. Make an ice table. There it is. So let's go ahead and knock that out. So 3.5 is going to be my concentration of ammonia. 0 and 0. And so again, minus X. I can ignore that minus X. Go ahead and write it down though, and just kind of circle it. That's how I do. It makes me feel better. Plus X. And I got X and X. So I'm gonna have X squared over 3.5, and it's gonna equal to that number I just erased. 1.9. Whatever. Cool. You're gonna have to tell me that in a second. So there's that. I'm gonna set it equal to that value you just said, but I don't know, my memory is not serving me well. So there's that. I'll give the number. 1.8 times 10 to the negative fifth. Okay. So 1.8 times 10 to the negative fifth. And that's going to equal X squared over 3.5. Or just X cubed, because I was feeling like it. No, that's not a thing. Don't worry. If it was a thing, it's just going to be a different button on your calculator. So whatever. It is 3.5, right? Yeah. Alright, cool. I'm going to multiply both sides by 3.5. So, times 3.5. And while I'm over here, I'll go ahead. No, I won't do that. 6.3 times 10 to the negative is equal to X squared. To solve for X, I take the square root of both sides. And when I do that, I get X is equal to 7.94 times 10 to the negative third. And so that is my, if you look back at your ice table, this is not hydrogen ion concentration, this is hydroxide ion concentration, right? So you can do two things here. You could, since you programmed the equilibrium constant for water, if you program that into your calculator, you could take that and you could divide by this, and you'd have the hydrogen ion concentration, and then you could take pH. I would rather take this, put it in my calculator, and then like subtract from 14. I think that's better for me personally. But you could do it the other way, because this is, look, hydroxide concentration times hydrogen ion concentration. And in any solution, don't matter, this is fine, is going to give you that 1 times 10 to the negative 14th. So you can do it that way if you want to. What do you prefer? You want to try that way? I like to subtract from 14. That's how I go. All right, so my POH is equal to the negative log of that. And so when I go to solve for the POH, I'm just going to hit on my calculator. And then the other thing is you already have this number in your calculator, so you hit negative log of the answer. You don't have to type anything else in, right? Y'all know that whole like negative log of the answer. And so I get my POH to be, and then see, I told you, I was like, you're going to get an answer around 2, which I didn't do on purpose, but that happens a lot for these weaker ones. So anyway, if you know you had a KB value, you had ammonia, it's a base, you get to this, you're taking a test, and you get an answer for pH2, that's not right. So you need to go, oh crap, I need to subtract from 14. So 14, well, let me do it this way. pH plus POH. You got to show your work on the AP exam. You don't, it's not worth it. It's not worth to do all this and then not get credit because you didn't show this. It's not worth it. So my POH is 2.1. So my pH is just going to be equal to 11.90, I think. Yeah. So, and that's for this lesson as hard as it gets. How does that make you feel? You okay? Alright, so I don't know if there's any more to this one. I feel like I'm almost done. There might be one more. Oh, I know what it is up here. So we got the right answer, and then you subtract, and it's basic. It's above 7. So let's see. Find the POH, and then find the OH concentration and the ammonium concentration. So this is, yeah. So oh, find KB. I was like, what? All right. So anyway, so I can set up KB. I need to write the equilibrium expression. I like to do that first. I just don't like to do a problem without like where I'm going. I don't like that. So anyway, let me get that out of my way. So KB is equal to, remember the water's not counting in here, and I have the ammonium and my hydroxide and my ammonia. And so I know that it has a pH of 8.75. So what would be the fastest way to find the POH? Yeah, so there's my 14 friend. So 14 minus 8.75. Now let me just write out the formula. Just do it. Oh, sorry. I'm like rearranging the formula first. So 14 is equal to the pH plus the POH. You, like 3 days ago, didn't know any of this. If you don't fill around that formula, then I hate for you. Write it down anyway. Okay? I just reminded your mind last week. None of this, but this has been a foreign language. So you need to write this stuff and repeat it, okay? Then it won't be a foreign language anymore. So anyway, 14 minus 8.75. And so that's almost 9. And I got a quarter left over. So that's right. Okay, cool. So this is my POH. So my POH is 5.25. And I ran out of room because I was like showing all my work. So I need to erase this because I'm not done. I haven't found, oh no, I have room. My hydroxide ion concentration, right? So my negative log of the, let me set it up. I need to set it up the other way. Let me write down 5.25 first. I'm going to confuse you guys. You mind if I do this? I'm out of room. That's too much stuff on that paper. I don't like that. So 5.25 is equal to the POH. And so POH, this is what I want. I just needed room to read. So the negative log of the hydroxide ion concentration. And so, you know, what we need to do here is we got to solve for this little guy. So I got 5.25 is equal concentration is what I'm looking for, right? And so what I need to do here, don't skip the step, it's worth your time. Divide by -1, divide by -1. And so I got -5.25 is equal to, sorry, I need to write my log out. The log of OH, and I gotta get that log to go away. I'm making this look really easy because, like, I'm showing you every single step. If you're kind of like already going, oh, I can skip that step, or I can skip that step, please don't do it. Don't do it. It's not worth it. It's not worth it. So anyway, 10 to the -5.25 is equal to, and those cancel, the hydroxide ion concentration. So come over to my calculator. 10 to the -5.25. So I got 5.62. My memory. I need coffee. Times 10 to the -6. There we go. What do they want us to solve for, KB? Okay. So we're not done. But hold that number for me. Yes, sir. Yeah, so they're going to be equal. They're going to be equal. So we're almost done. This is real simple from here. Because we know the molarity of the solution. That's going to be the bottom of the fraction. And the top of the fraction is this square. I mean, I don't need to go back to it. Maybe we can just do it if you want to. We're already up here. So 5 points. Just tell me that number in a second, okay? So KB was equal to, this was the NH3 one. Am I making that up? What was the molarity of it? Okay, so 0.15 was my concentration of ammonia. And then up here I had 6.25. I don't know what's wrong with me. I honestly drink about like 6 cups of coffee a day, and it makes me super smart and great. I can't remember like what I just wrote down. So it's right here. I'm just gonna stare at it. So 5.62 times 10 to the -. I'm telling, this is bad, you guys. -6, and because the hydroxide and the hydroxide and the ammonium are the same, I'm just gonna square it. If that's tripping you out, I'm kind of sad I skipped a step, so I can write it. So and the reason that these are the same, every time you break an ammonia apart, you get one of those and one of those. 1 to 1. Okay? I just filled that in. And now you can just plug that in your calculator and solve. Okay? So I just got, oh, I didn't, I hit the wrong button. Forgive me. Alright, so I got 2.10, or maybe 11, yeah. Times 10 to the -10. That's my KB value. So we just basically, this one, we went the other way with it. You know, they started out with the POH or pH, and you gotta talk yourself through it. And then, you know, this is cute, you have a formula sheet, but you can tell that when I start adding some acid and a base, one's weak, one's strong, and then you gotta find where you are in this, and then, so don't skip steps, think your way through it, and then we're every day just gonna add a little bit more, but so far, how's this going? It's okay. We need some practice time, don't we? So let's do that. Maybe there was like 1 or 2 more slides, I feel like. Nothing crazy. So make sure we got it right. And that was our KB value, so good for us. Yeah, okay. So polyprotic acids. That's a crazy word. Let's break it down. This means it has many protons. What are the protons? Hydrogens, right? So that just means that you have more than one hydrogen. The biggest thing with this, like sulfuric acid or carbonic acid, they are going to donate more than one hydrogen in a solution. It's really important for you to know, though, that they do that one at a time. Now look at these numbers here, okay? This is my carbonic acid. It's going to donate one hydrogen, and this is its own reaction, okay? So anyway, Ka value for this one is times 10 to the negative 7th. So this is not a strong acid, but 10 to the negative 7th is pretty pretty weak acid. But if we look at the second one, the Ka value for the second donation of a hydrogen is 10 to the negative 11th. The first donation of a proton always for a polyprotic acid is going to be a stronger acid. For example, something like sulfuric acid. Sulfuric acid is a strong acid. It dissociates completely, but it dissociates into hydrogen and then HSO4 with minus. That's a strong acid. HSO4 minus, that's also an acid, but much weaker. Okay, so you're going to donate two completely different reactions. And if I go to neutralize this acid, it's going to be whole reaction, whole titration curve, you don't know what I'm talking about yet, and then a whole nother one. I'll show you that, and then I'll call it a day. Well, not really. I can't say it with a straight face. So yeah. Ooh, highlight this. They're going to trick you with this. I've seen this trick. When you go to calculate the pH of these, do you know how I just gave you the two acid dissociation constants? I just gave you those. If you're going to pause it, you can stand up. So anyway, if you can look at those, and so if you're going to calculate the pH, we've got to do that whole ice table because they're both weak acids. But we're going to solve using the Ka for the first hydrogen donation. So we're going to do the whole ice table thing, and then if you set it equal to this second one, if you set it equal to this guy, your answer is going to be wrong. Okay, so if you want to calculate the solution of 1.2 molar carbonic acid, you're going to need to set your ice table and everything equal to this first one. That second one don't mean anything. It's so weak it doesn't matter. Okay, so anyway, there. That looks so good. I want to show you something. I want to show you a titration curve. I want to show you the titration curve I did during my planning period. It is perfect. I mean that. Are you excited? Can I show you? Okay. Who said no?